In this video, we're talking about tangent and secant segments of circles and how we can use those types of segments to create new rules for a circle to help us solve problems. So yes, we're introducing even more rules about circles. You might be overwhelmed, you might be drowning, but it is what it is. We've got to get through it. So, time to tighten the belt. Crying and being upset is not going to help, so we got to get over it. So let's get started. Below, PS is called a tangent segment because it is a tangent that it touches a circle in exactly one point. PR is called a secant segment because it touches a circle in two spots. And then PQ, from here to here, is called an external secant segment because it's part of the secant segment, PR, but it's also external because it's on the outside of the circle. So just a few definitions to get us started. That's going to look a warm-up. Now that we're warmed up, let's introduce a few new rules. If we have two secant segments that share the same endpoint outside the circle, then what we can do is multiply different pieces together. In particular, if you're following the letters, it's not that bad. But what's happening here is that the external secant segment AB times the total secant segment EB, if you multiply those two pieces together, then that's going to be equal to the external secant segment EC times the total secant segment ED. Okay? So again, very similar, but we got external times the total is equal to external times the total. So let's use that information in example 30. So in example 30, I have two secant segments. I know they're secant segments because each segment touches a circle in exactly two spots. And I have a rule, it's right here above. We know that the external times the total is equal to the external times the total. Okay, so now I'm just going to use that information and set up my rule using letters. So again, it was external, so RP times the total RQ, and that's equal to, based on this rule, the external RS times the total RT. As soon as I have my equation set up like this problem gets a heck of a lot easier. All we got to do is plug in our numbers that we're given. Alright, so my external piece in green was 9. That goes in for RP. RQ was 9 plus 11, which is 20. Again, 9 is on the outside, 11 on the inside, so that total length was 20. And we know that's equal to RS, which was 10, times ST, which was X. Alright, so now let's fill in what we know and simplify as much as we can. 9 times 20, that's 180. If you need to use your calculator, use it. So I have 180 equals 10x. I want to get x by itself, so I'm going to divide by 10. So x is equal to 18, and it goes here. No big deal, pretty easy. Again, the hardest part is just setting up the equation itself. Once you do that, you've got it made in the shade. Let's keep going. If a secant segment and a tangent segment share an endpoint outside the circle, then we have a new rule. Okay, so again, we'll just talk about it real quick. EA is a tangent segment because it touches the circle in one spot. ED is a secant segment. Okay, so what we can do is say EA, which is the part outside. If we square that piece, then it's going to be equal to the external piece times the total piece. That's what we're saying. So what we're going to do on the next example is use this rule again. It's the tangent squared is equal to the external secant times the total secant. Okay? Example 31, we're doing this exact same thing. We have a tangent because it touches in one spot, and a secant because it touches in two spots. Again, the tangent squared is equal to the external times the total. Okay? I'll say that again. The tangent squared is equal to the external secant times the total secant. Okay? So I like to do those lines of different colors to help me get my thoughts together and figure out what my equation needs to be. So again, I said it was the tangent squared, so BA squared is equal to the external BC times the total BD. As soon as I have my equation, I'm going to start plugging in my numbers. I know my tangent was 5, so I have 5 squared equal to my external piece. In this case, it was x times the total piece. So my total piece is x plus 4. Okay? Because my total piece, I just added these two together. It's more than one thing, so it must be in parentheses. Now I'm ready to start cleaning this up. 5 squared is 25 equals, now I have distributive properties. So I'm going to multiply it out. X squared plus 4x. Okay? And I can solve this by hand, but I'm going to solve it by graphing because we haven't done that in a while. So let's solve it by graphing. What I'm going to do is say left side y1, right side y2. So I have 25 equals x squared plus 4x. Graph it. I'm starting a new picture, so I'm going to hit zoom 6. All right, now, I only see one piece, but I know I'll graph 2 pieces, so I need to zoom out, actually. Now I have 2 points of intersection. So I'm going to find the one on the left first, so second calc, option 5. First curve enter, second curve enter, and guess. Put my cursor in position. I get it for my first point of intersection, x equals, and I'm rounding here, so x equals negative 7.39. For my second point of intersection, I'm going to repeat the process. Second calc, option 5. First curve enter, second curve enter, guess. Move your cursor into position. So I get 3.39. Okay. Now I do have 2 answers. However, I want to realize that x is a distance, and you need to ask yourself, can distance ever be negative? To answer that question, just ask yourself, does it make sense if I tell you that I ran negative 5 miles last night? Can you run a negative distance? Absolutely not. So distance can never be negative. So even though there's 2 algebraic answers, in terms of the problem, the only answer I want to worry about is the positive one. So x is 3.39. Again, that's an approximation. You could have solved this by hand. I'm not going to put you through that. But if you want to, you know what it should be, so go through and do that. And that's it for this video.